For nearly half a century, Voyager 1 has been traveling farther than any human-made object in history, quietly slipping beyond the reach of the sun and into a region we once thought was almost empty. Built in the 1970s, designed for a mission of just a few years, this fragile machine is still talking to us after 45 years in space. And what it is telling scientists now is deeply unsettling. Voyager 1 has reached a boundary no spacecraft was ever meant to study directly, and the data coming back does not fully match our models, our predictions, or our expectations. Tonight, we are going to uncover what Voyager 1 discovered, why scientists describe it as impossible, and how this single probe is forcing us to rethink the true nature of interstellar space. Voyager 1 is a spacecraft that should have died decades ago. It was born in the 1970s at a time when computers were primitive. Memory was measured in kilobytes and data was stored on 8-track magnetic tape. NASA never imagined this probe would still be operating 45 years later, let alone sending back discoveries that challenge modern physics. Voyager 1 was launched because of a once-in-176 years planetary alignment that allowed it to steal speed from the gravity of the giant planets like a stone skipping across invisible hands in space. That gravitational choreography pushed Voyager 1 past Jupiter and Saturn, revealing volcanoes on Io, cracked ice on Europa, and a solar system far more dynamic than anyone expected. But once its original mission was complete, Voyager 1 did not slow down, did not stop, and did not fade into silence. Instead, it kept moving outward farther than any human creation before it, quietly transforming from a planetary explorer into something far more important, humanity's first true interstellar scout. For decades, scientists argued about where the solar system really ends. The heliosphere, a vast bubble inflated by the solar wind, was supposed to form a clear boundary between the sun's domain and interstellar space. Models predicted a sharp transition, almost like crossing from calm water into a different ocean. Voyager 1 was expected to detect a dramatic shift in magnetic field direction the moment it crossed that line. Instead, something deeply confusing happened. As Voyager 1 approached the heliopause, it detected an enormous increase in plasma density, nearly 80 times higher than before, a clear signal that it had entered a new region of space. But the magnetic field did not behave as predicted. Its direction remained strangely aligned with the sun's field when theory said it should have twisted dramatically. This was not a minor discrepancy. It meant the boundary between our solar system and the galaxy was not a clean edge, but something layered, tangled, and far more complex than anyone had drawn on paper. This is where Voyager 1 made its so-called impossible discovery. The data suggested that the heliopause behaves less like a wall and more like a turbulent shoreline where solar and interstellar forces mix instead of separating cleanly. Magnetic fields fold into one another. Charged particles swirl unpredictably. Instead of stepping into a new environment all at once, Voyager 1 appeared to drift through overlapping regions where solar influence still lingered even as interstellar plasma dominated. This directly contradicted long-standing theoretical models. Scientists had to accept an uncomfortable reality. They had misunderstood the shape and behavior of our solar system's protective bubble. Voyager 1 was not just confirming predictions, it was rewriting them. The boundary of our cosmic home was not static, not symmetrical, and not stable. It was alive, dynamic, and shaped by forces far more chaotic than expected. What Voyager 1 revealed has consequences far beyond academic theory. If the heliosphere is porous and turbulent, then our solar system is far more exposed to galactic radiation than previously believed. Voyager 1 showed that cosmic rays from outside the system penetrate deeper and interact more intensely with solar particles than expected. This matters because the heliosphere is the shield that protects every planet, every spacecraft, and every form of life here on Earth from the full violence of the galaxy. Voyager 1's findings suggest that this shield breathes, shifts, and weakens depending on conditions we are only beginning to understand. The discovery forces scientists to rethink long-term space travel, radiation exposure, and even how common life might be elsewhere in the galaxy. Voyager 1 did not just find something unexpected. It exposed how little we truly knew about the space we thought we understood best. What truly unsettled scientists was not just that Voyager 1 crossed into interstellar space, but that it did so in a way no model had accurately predicted. For years, theoretical simulations described the heliosphere as a relatively smooth, balloon-like structure, expanding and contracting with the sun's activity cycle. According to those models, the heliopause should shift significantly depending on whether the solar wind was strong or weak. Yet, when Voyager 1 reached this boundary, it did so at a distance remarkably close to what Voyager 2 would later measure years afterward, despite completely different solar conditions. This alone shattered the idea that the heliosphere behaves in a simple rhythmic way. Instead, Voyager 1 revealed a system that resists prediction, where large-scale stability hides intense small-scale chaos, forcing physicists to admit that their understanding of how stars interact with the surrounding galaxy was incomplete. One of the most powerful analogies scientists now use to describe Voyager 1's discovery is that of a shoreline. Instead of a solid wall separating the solar system from interstellar space, the heliopause behaves more like a coast where two oceans meet. Solar particles push outward, interstellar matter pushes inward, and the result is a region of turbulence, mixing, and constant motion. Voyager 1 detected twisted magnetic fields, fluctuating particle densities, and irregular structures that resemble waves crashing and retreating. This means the sun does not simply carve out a clean bubble in the galaxy. It negotiates with its environment continuously. The boundary shifts locally, folds over itself, and creates pockets where solar and interstellar influences coexist. Voyager 1 was not crossing a border, it was navigating a stormy transition zone no one had ever directly measured before. As Voyager 1 moved deeper beyond the heliopause, another disturbing pattern became clear. Galactic cosmic rays increased dramatically, confirming that interstellar space is saturated with high-energy particles capable of penetrating matter and damaging both electronics and biological tissue. Inside the heliosphere, these particles are partially deflected by the sun's magnetic field. Outside, there is no such mercy. Voyager 1's data showed that this radiation environment is not occasional or directional, it is constant. This discovery has enormous implications. It suggests that the galaxy itself is far more hostile than previously assumed, and that planetary systems like ours rely heavily on stellar bubbles for long-term stability. In other words, life-friendly environments may be far rarer not because planets are uncommon, but because effective cosmic shielding might be. Perhaps the most remarkable part of this story is that Voyager 1 is still teaching us anything at all. Built with technology millions of times weaker than modern devices, operating with fading power and instruments slowly being shut down to conserve energy, the spacecraft continues to deliver discoveries that reshape astrophysics. Researchers analyzing Voyager 1's data today are often younger than the probe itself, using modern tools to